Having with us Professor Emmanuel Breuillard, I hope I got the pronunciation right, who is at Oxford as the Sadlerian professor. Okay, in direct contrast to the Brexit. But so he will speak on approximate lattices and quasi-crystals. So over to you.
All right. Thank you. Thank you very much for the introduction. Let me thank the organizers for this invitation and congratulate Raghunathan for his birthday. As the title suggests, I will speak about approximate lattices and quasi-crystals. So I will discuss work by Simon Machado, Ehud Ruszowski, and Michael Björklund and Tobias Hartnick. So Simon Machado is a student of mine, and we've been discussing these things in the last few years. He hasn't graduated yet. So, all right, so let me maybe first introduce a little bit the subject. So we all know about lattices in Lie groups, and maybe one of the reasons we study lattices in Lie groups is because they are fundamental groups of interesting manifolds, and we'd like to understand the geometry of these manifolds. But maybe another motivation for studying lattices comes from the fact that there are discrete subgroups in ambient Lie groups or locally compact groups. And they also provide, therefore, tilings of these spaces, and they give many nice pictures in particular. So if we go in this direction of tilings, one may be tempted to maybe remove the property, the condition that the discrete group is a group. So I'm going to tell you about the notion of Deleney set. So Deleney set in a space, let's say X here, XD is a locally compact matrix space, which I assume is a homogeneous space where I have an isometric group acting transitively. So I really think of the classical example of the Euclidean space or the hyperbolic space, or more generally, you can take a locally compact group with a left invariant metric. And so a Deleney set is basically just a discrete subset in it, which has two conditions. It's relatively dense. So every point in the space is at a bounded distance from a point in the set. And it's uniformly discrete. So this means that there is a fixed radius such that any ball of that radius contains at most one point from the set. So I'm going to define to give four definitions where I will define a class of Deleney sets, subclasses, so a hierarchy of more and more precise, constrained family of Deleney sets. So of course, the Deleney set is, the notion of Deleney set is very general, and there is no rigidity at all. So you can just basically arrange points in a way so that they satisfy those two conditions in a very easy way. On the other hand, when people study tilings, they usually impose this second condition here, this definition 2, where they say that the Deleney set has finite local complexity if additionally you assume that what you see around every point at a given distance has only finitely many isometry classes. Okay, so if you fix a ball around a point in the set, then you see finitely many points, and these finitely many points can achieve only finitely many configurations up to isometry. So we call this FLC for finite local complexity. And it's a remark that essentially the FLC Deleney sets in the isometry group of my space essentially correspond to tilings of the space with finitely many prototypes that are translated by isometries and local matching rules that make sure that you can have only finitely many configurations in a local, in a fixed ball. So it's also easy to see that a Deleney set is FLC, essentially if and only if the lambda inverse lambda is closed and discrete. So it's a locally finite set in the group G. That's just a reformulation of the definition. And from this, you can see that already there is some interesting rigidity here, in the sense that the group generated by lambda inverse lambda, the subgroup in G, has to be finitely generated. Okay, so that's easy to see because it's going to be generated by the because you have only finitely many configurations, by the differences between two elements in lambda at a finite large enough distance, assuming that you're relatively dense, you can do that. So you have this sort of property. However, here is an example showing you that this FLC property is still not very rigid. So here's an example. So take a uniform lattice, discrete co-compact subgroup in a product G cross H, and consider a Course-Lie Lipschitz maps from G to H. Suppose you have some like this, and for every point in G, you pick a point gamma G in the lattice, which is at bounded distance from this graph, the graph of phi. And then you project that point to the first factor, and what you obtain is a FLC Deleney set. So you see that since in different situations there can be many such phis, then you can construct this way many FLC Deleney sets and many times. So the third definition, I'm going to again restrict, given a further condition on the Deleney set, is that of approximate subgroup. So this is a very general definition which occurs in many branches of mathematics, in particular in combinatorics. So if you have a group G, then a subset lambda of the group G is said to be an approximate subgroup if first of all, you assume that one is in the set and the set is symmetric, lambda is lambda inverse. But the defining condition is that the product set, lambda times lambda, can be covered by finitely many translates of lambda. And so this set X here is a finite set of size at most K. And this K sort of quantifies the quality of approximation. So of course, if K is 1, then you have a genuine subgroup. Otherwise, we have what you call an approximate subgroup. So for this reason, you see that lambda times lambda will be, if you start with a Deleney set, which is also an approximate group, then lambda times lambda will be locally finite, and therefore it would be FLC. Okay, so the Deleney sets that are also approximate groups are FLC Deleney sets. And we'll see that the converse actually does not hold. So for the remainder of the talk, I will say that a Deleney set, which is also an approximate subgroup, I will call it a uniform approximate lattice. Okay, so an approximate lattice is a Deleney set, which is also an approximate group. And I call it uniform because later I will define non-uniform versions. So before I go further, I want to motivate a little bit the introduction of approximate subgroups there by this proposition here, this remark, which is that, in fact, if you have a Deleney set, which is assumed symmetric, such that the triple product, lambda times lambda, is discrete and closed, so locally finite in G, then, in fact, this implies that lambda is an approximate subgroup. Okay, so triple products are needed, while before, for FLC, we had double product. Okay, so that's a difference. So if you assume that the triple product is discrete, then it's very simple to check that lambda has to be an approximate subgroup. And indeed, because lambda is Deleney, you can write G as K times lambda for some compact set K. And therefore, lambda times lambda is contained in K times lambda. But the element of K that you get here must be in lambda times to the 3, right? Obviously. And this is locally finite, so it has to be a finite set. Okay, so that's the third property. So here's an example, an example on the real line. So you take the real line and you take a number field in the real line, and you look at the set of elements of the number field that generate the number field and are also Piso-Vichaya-Raghavan numbers. Okay, so these are the numbers that have that are bigger than 1 and have all their other conjugates in the unit circle. So this is an example of an approximate lattice in R+. So the fourth subset, subfamily of Deleney sets is the so-called cut and project sets. So these are obtained in the following fashion. You start with your group G, and you pick another locally compact group H, and you pick a co-compact lattice in G cross H. And then you intersect this co-compact lattice with G cross a compact neighborhood of the identity, W naught, all right? So, and then you project this intersection to lambda, to G, okay? So you have a slice in the product, you have a slice, you thicken it a bit, you look at the lattice points there, and you project to G. So if W naught is large enough, then it's easy to see that this is going to be relatively dense and discrete and uniformly discrete. So this is going to be a Deleney set, and in fact, FLC. And in fact, if W naught is symmetric, then it's actually going to be an approximate subgroup. Okay, so it's really a subclass. So what happens if you change W naught into another W naught prime? Then what you get is a commensurable subset in the sense that, so that won't change things very much, in the sense that every, in the sense that the new cut and project set is covered by finitely many translates of the first one. And everything in this talk, I will deal with things up to commensurability. Okay, so to summarize what we discussed so far, we have defined families of Deleney sets, and the more constrained family is the family of cut and project sets, which implies that they are approximate subgroups, which implies that they are FLC. So the natural question is to ask what to do. Can these implications be reversed? So let me give you some examples. So here, this is familiar on the left-hand side. This is called the pinwheel tiling due to Conway. This is substitution tiling. Here's a triangle with 1, 2, and square root of 5 the length of the sides. And you can decompose it into 5 pieces with the same triangle, just smaller. And you keep going this way, and what you get is a tiling, which by subdividing and blowing up, you get a tiling of the plane. And that's it's easy to see that this is FLC, but in fact, it's not an approximate subgroup. The reason being that the angles, so this angle is not a rational multiple of pi, and so you're going to get a dense set of angles of directions in the size of the triangles that show up. On the other hand, on the right-hand side, you have the so-called Penrose tiling, the famous aperiodic tiling of the plane, and this is an approximate group. It comes from a cut and project construction, as was noticed by De Bruyne in the 1980s. So this is 2 examples. So now let me move on to the second part of the talk, where I will discuss a theorem of Yves Meyer from the 1970s, which says something about these implications. So here, let me go back to there. So the pinwheel tiling shows that this implication cannot be reversed, and we'll be interested in the talk about this implication here. So can this implication be reversed? And we're going to show that in many cases it can. So what Meyer did in the 1970s is that he actually showed that this is indeed, this implication can be reversed up to commensurability for Euclidean Deleney sets. So he showed the following. So if you have a Deleney set in Rn, the following are equivalent. To say that lambda minus lambda is uniformly discrete, to say that lambda is an approximate subgroup, and to say that lambda is actually contained in a cut and project set and commensurable to cut and project set. So the equivalence between 1 and 2 are easy. In fact, I think Meyer did, he was first looking at a triple sum here, and Lagarius noted that you can assume only that lambda minus lambda is uniformly discrete. So many proofs of this theorem have been have appeared since. There's a nice paper by Moody that discusses this. But the main point of the proof is to show that if you are an approximate subgroup and a Deleney set in Rn, then you come from a cut and project construction. So Meyer did this in the 70s, and in between the 1970s and the 1990s, physicists identified in nature quasi-crystals, and they were unaware of the work of Meyer, and later in the 90s, the two communities realized that in fact Meyer had proven this theorem, and then Meyer called such sets quasi-crystals or mathematical quasi-crystals. Why? Because quasi-crystals are those Deleney sets for which the Fourier transform of the counting measure looks like has pure spectrum, so is a linear combination of Dirac masses. And indeed, he showed that these sets have this property. So the proof that of Meyer is not very difficult, but the main point is to realize that if you are an approximate subgroup, then the injection from lambda to the group it generates, which we know is finitely generated, so because it's FLC, is a quasimorphism. Okay, and it's well known that quasimorphisms in abelian groups can be corrected to actual morphisms, to linear maps. And once you have corrected the quasimorphism, then you have a splitting of RK, and this gives you the cut and project construction. So I should mention also that Meyer had a fourth equivalence here in terms of what he called harmonious sets in Fourier analysis. So yes, so the question which I want to address in this talk is a set of questions posed by Björklund and Hartnick. And the question is very natural, is the following. So first of all, can we classify Deleney approximate subgroups of Lie groups, so approximate lattices? And second, does Meyer's theorem extend to other groups? So in other words, if you have an approximate subgroup which is the Deleney set in another locally compact group, does it come from a cut and project construction? And so I gave this problem to my student Simon a few years ago in his master thesis, and he solved it for Neopotent Lie groups. And he showed that in fact, indeed, Meyer's theorem extends to Neopotent Lie groups exactly as it's stated. So every approximate lattice in a Neopotent Lie group comes from a cut and project construction. And a corollary of this is that you may wonder, given a Neopotent Lie group, what are the conditions for it to admit some uniform approximate lattice? And it turns out that this is if and only if the Lie group, the Lie algebra of the Neopotent Lie group has algebraic structure constants. So this is a reminiscent, or it's a generalization of Malsev's theorem, which is proven in the second chapter of Raghunathan's book, and which says that for Neopotent Lie groups, admitting a lattice is the same thing as saying that the Lie algebra has rational structure constants. So yes, so this is for Neopotent Lie groups. The proof of Machado, so by now he has several proofs, but the first proof actually mimics Meyer's proof by looking at the Lie algebra and looking at quasimorphisms in the Lie algebra, showing that they preserve the Lie bracket structure and so on. So, but to tackle other groups, one has to first make an observation, which is on this slide here, and has to do with the notion of good model for approximate groups. So this is a notion which was introduced by Hrushevsky in about 10 years ago in his work on pseudo-finite approximate groups, and which was crucial in later work of Green and Tao and myself, where we gave a structure theorem for finite approximate groups. So of course, finite approximate groups, you may say, you know, by the definition I gave, every finite set of a subgroup is, every symmetric finite set is an approximate group. But what's interesting here is when you fix the parameter k and let the finite subset be very large, and then you can have a structure theorem. This is what we did. But this work only was concerned with a finite approximate subgroup, while now we are only concerned about infinite approximate subgroups. So this notion is the notion of good model. So the way the structure theorem for pseudo-finite approximate groups was proven was, I mean, deep down, the key idea was to try to build a certain topology on the finite or the pseudo-finite approximate group by essentially building a certain fine structure on lambda, by showing that lambda has, so this is what I explained here, and this idea goes back maybe to the work of André Weil in his work on uniform structures. You're interested in finding a sequence of approximate subgroups of your given approximate group, which of smaller and smaller approximate subgroups that are still commensurable to the original one, and also every conjugate is still commensurable. And so if you have such a thing, then you have what's called a good model, and a good model is a homomorphism from the group generated by lambda to some locally compact group H, such that the image of lambda is relatively compact, and lambda contains pre-images of a small neighborhood around the identity. So this gives you the topology on H will pass on to a topology on lambda, and will therefore define this family of neighborhoods of the identity in lambda, so to speak. So it's very easy to see that if you come from a Cartan project set, and you are now a Deleney set, which is an approximate group, if you come from a Cartan project set, then the second factor, H, provides a good model for you, because this gives you this topology that you're looking for. And conversely, if you have a good model and you are a Deleney set, an approximate group, then the subgroup generated by the graph of this good model is discrete. And because lambda is Deleney, it's going to be a uniform lattice in the product G cross H. So actually what we are trying to do is to build a good model for Deleney approximate groups. Okay. So we, at the beginning, we had no idea how to do this. And let me now move on to, now we of course want to tackle this question for semi-simple V groups. And so before I go there, let me just say that we can also define, move away from Deleney sets and consider non-relatively dense discrete subsets, and define this notion of non-uniform approximate lattices. So there are two possible definitions. There is a nice paper of Björklund and Hartwig where they discuss possible definitions, what this could be. So there is a very natural one due to Hrushevsky, which instead of relatively dense, you assume that it's uniformly discrete, and that there is a, so to speak, Borel, so to speak, fundamental domain for lambda. So it is this condition 2 here. While Björklund and Hartwig had a different idea, they thought that maybe we should impose as a condition to be an approximate lattice that there exists a G-invariant measure on the invariant hull, which is the G orbit of lambda in the Chaboty space of closed subsets of G. So it's not easy to see what's the relation between these two conditions, but Machado proved that in fact B implies A. So it's a good name. That strong is a good name. That B implies A. So indeed, yeah. So every strong approximate lattice is an approximate lattice. So it turns out in the end that in certain cases, so for example, for semi-simple Lie groups, the two are equivalent. I should mention also that Bjorklund, Hartnick, and Pogorzelski prove that cut and project sets coming from lattices are always strong approximate lattices. Okay, so now I come to the statement of one of the main statements. So which is generalization of Meyer's theorem to simple Lie groups. So here is Machado's theorem. So the setting is a simple Lie group. So you have a simple Lie group of higher rank, and you start with a strong approximate lattice in there. And the conclusion is that in fact G lambda is contained and commensurable to a cut and project set. So in other words, Meyer's theorem extends to strong approximate lattices in higher rank simple Lie groups. Okay, so some remarks. So actually, his proof and his theorem stated in a short version, but it actually works in the aesthetic case where G can be replaced by the product of algebraic groups of a local field where the algebraic each factor has higher rank. Okay. All right. So while he was doing this, Hruszczowski came up with a completely different argument of the same theorem, in fact, a stronger theorem, which in particular, he was able to remove the assumption of high rank. So in fact, also in rank 1, or if you have rank 1 factors, the theorem holds. So this was actually, that it holds in rank 1 was quite a surprise to us, because we thought that maybe in groups like SL2R, you could, you may be able to deform approximate lattices. And it turns out that you cannot, unless your approximate lattice is a genuine lattice. So in particular, this theorem holds, and it holds not only for strong approximate lattices, but it holds for all approximate lattices. So the two proofs are very different. Machado's proof uses ergodic theory, and Hruszczowski's proof essentially uses model theory. So let me say a few things about the proof of Machado. So the idea is to mimic Margulis's proof of arithmeticity, because you see, proving this converse of proving this generalization of Meyer's theorem is essentially a Margulis type theorem, an arithmeticity type theorem, because in the end, because the groups are high rank, and also because just the product G cos H is high rank, then every lattice there we know by Margulis is arithmetic. So this means that every approximate lattice actually has an arithmetic origin. So this is why, hence the name arithmeticity. So the proof of arithmeticity goes through a superioridity theorem, which is here, which is essentially just the same statement as Margulis' superioridity under these assumptions, except that here you start with a representation of the group generated by lambda, and the dichotomy is either the image of lambda is bounded, not the group generated by lambda, but the image of lambda, or T extends to a continuous group homomorphism. So the proof again is based on Margulis's ideas, and using this cocycle. You look at cocycle by choosing a Borel section from the invariant Hull. So the proof uses quite a lot the fact that the invariant Hull has an invariant probability measure. So it's and the rest is just some comments on the proof, which again, in the case, so you use superioridity in at least two places to prove arithmeticity. Also, in the case when you're not Deleney and you're not uniform, you have to prove that you're finitely generated, and this can be done by using some version of property T for approximate lattices. So maybe in the last minute, I would say one thing about Hruszczowski's approach. Hruszczowski's approach is quite different, and instead of applying ergodic theory, he proves a very general amazing very general theorem about arbitrary approximate groups, showing that, of course, arbitrary approximate subgroups do not always have a good model, but he shows that they always have a good quasi-model, namely that the map we had before, which was homomorphism, is no longer a homomorphism, it's only a quasi-morphism. And the defect of the quasi-morphism lies in a certain abelian group. So with this very strong theorem, he then is able to prove the arithmeticity, I mean, the converse to Mayer's theorem, that they are contained in cut-off project sets. And then you can apply Margulis' theorem in its original form to deduce arithmeticity. So I should stop there, maybe mention a few further directions and a list of references for those interested in this topic. Thank you very much for your attention.
Thank you, Professor Breuillard, for a very nice, interesting talk. Are there any questions or comments? Okay. If not, let's thank the speaker once again.
I think Professor Gopal Prasad wants to ask something.
Yeah, no, I'm just saying that, I tried to learn the theory of approximate groups, but didn't succeed. Maybe one has to make another attempt. So it looks difficult, but, your talk was very interesting. And I hope that this will provide impetus for my attempting again to learn the theory.
Thank you, Professor Gopal Prasad. Thank you.
Nice to see you, Emmanuel.
Nice to see you. Yes, nice to see you.
I have some question. You introduced this Piso-Vijayaraghavan numbers as an example. So, is there some application to such kinds of arithmetic things? There are this conjectures about the smallest Piso-Vijayaraghavan should be bounded away from 1 and such things.
Yes, I don't think there are applications, but maybe it goes the other way. But I think you mentioned talking about maybe the Lemmer conjecture. Or
yeah, right.
like that.
Right. Salem number problem. Oh, yeah, right. Yeah.
Right. No, I'm not aware of applications, but certainly I find it fascinating that these PV or PVS numbers show up in this area. Yeah.
Okay.
So yeah, so you can show actually that these approximate lattices always commensurable to, for example, if you're in SLNR, then they will be commensurable to the set of points in SLNR, which whose matrix entries are all Piso-Vijayaraghavan numbers.
Oh, okay.
Yeah.
I also had some other, but probably you did mention something about, I don't know that the question is well posed, but is there some harmonic analysis way of looking at this approximate lattices? You did mention something in the.
Yes. So this is the notion of harmonious sets. Which measures to what extent an abstract character, so group homomorphism, from the group generated by lambda to the circle group can be approximated by continuous homomorphisms. So if this can be done, then this is called a harmonious set, and Meyer showed that the two are equivalent. So being harmonious and being coming from cut-off project construction,
Okay.
And being a what he calls a quasi-crystal.
Okay. Thank you. Yeah. Are there
so there are lots of other interesting questions, such as trying to understand the the Fourier transform or the non-abelian Fourier transform in SL2R. So there's some nice work by Bjorklund, Hartnig, Pogorzelski, a series of papers where they study from the harmonic analysis point of view, the Fourier non-abelian Fourier transforms of the counting measure on such Deleney sets.
Okay. Are there any further questions or comments? So let's thank the speaker.